Okay, we're continuing on chapter 12 here, which is kinetics. So we started talking about kinetics last time. And remember that kinetics is really the study of, the rate of reaction, sort of how fast or even slow a reaction proceeds. And as we talked about last time, we'll talk about thermodynamics a little bit later on in the semester. And that deals with the idea as to whether or not a reaction will actually take place. But kinetics really does deal with that aspect of, how fast or slow it does happen. When we think about a reaction, as we talked about the other day, we do assume that in this type of reaction that it is heading toward the product side. And what we would expect to happen over time is a decrease in the amount of our reactants. And we would expect an increase in the amount of our products, as obviously to make our products, we have to use our reactants up to do that. And we talked about that you can write what is sometimes referred to as a rate expression. And a rate expression is really how a concentration is changing over time. And that could equal the average rate of the reaction will equal minus 1/2 in this example here, change the concentration of A over the change in time. A couple of reminders of some of that. We talked about the idea that to take care of the stoichiometry part of the calculation, we do 1 over the coefficient. So again, that is where the 2 comes from. In addition, because this is a reactant, it should be decreasing with time, which means it will have a negative value for how it's changing. And that is because when we do the change in the concentration of A, which is our reactant, the concentration of A final minus the concentration of A initial, the final concentration actually should be a smaller number than our initial concentration, again, because the amount of reactant should be decreasing with time. And that's going to yield us a negative number here when we do sort of that part of it. And that negative and the negative in front will turn our rate here into usually a positive number for the average rate of the reaction. So again, that's important to keep that in mind. We could also set this equal to our product side, which would be 1/3 change in the concentration of B over the change in time. Once again, here, the 3 comes from the coefficient, and that takes care of the stoichiometry part. Again, we do not have a negative sign here. It's positive because it should be increasing with time. And that, again, is because when we take the change and say the concentration of B, which is our product here, when we do our final concentration of B minus our initial concentration of B, this actually is the larger number, and this would be a smaller number. And that's going to give you obviously a positive value here, and our positive value here, once again, will give our rate a positive value. So you do want to be careful with this in terms of the signs. So you do end up with the correct sign on whatever you're doing. And you always want to do final minus initial. So that should give you sort of your correct sign when you do that part of the calculation. We could set all these equal to each other, which, as we talked about, we did some examples, allows you, if you really just know one piece of information about the actual reaction that's taking place, if you know how a reactant is changing over time, you know how a product is being made over time, or even if you just know the average rate of the reaction, you pretty much can figure out how everybody in that reaction is changing over a period of time. Remember, I also talked about sort of that's usually the average rate for the overall sort of run of that reaction. Remember, though, that there are instantaneous rates which can vary throughout the reaction. At certain points, it may run faster. At certain points, it may slow down. And again, I think I did the driving example, right? On average, you may drive 65 miles per hour, but there may be periods there where you're driving faster or slower if you kind of just clock it for that period of time. And those would be more of an instantaneous sort of rate. We also talked about after that, that we talked about the rate law, and the rate law looks something like this, that the rate is equal to K times A to the X and B to the Y. A couple of things about the rate law is it only involves reactants. So reactants are typically the only things that are usually placed in a rate law. These guys here are referred to as the orders. And K is the rate constant. And you can kind of think of that as sort of how fast or slow a reaction is taking place. Again, something with a large rate constant would probably happen really quick. And so there's a smaller rate constant would be a slower reaction. The orders are always found experimentally. So the rate law is always found experimentally, which, as we talked about, basically means you typically will be given a table of values of your reactants, and you'll usually have some initial rates given to you and a bunch of experiments that were done. And we could use the sort of experimental data that's in these tables to allow us to calculate the rate law and the orders. We could do that most often by sort of a calculation where it's rate 2 over rate 1 equals K A to the X, B to the Y, and K A to the X and B to the Y. So remember that when you kind of go to this table, however many entries they may have in that table, the goal is to really find 2 entries where one of the reactants remains constant and the other one varies. If you happen to have 3 reactants, you would then want to find 2 entries where 2 stay constant and 1 vary. The idea is to just have 1 variable, right? So you have 1 unknown to solve for, and you can plug those in there. A couple of helpful things a lot of times to plug sort of the larger value for the rate up on top. That usually will give you kind of prettier whole numbers. And at some point you may get something like, 4 equals 2 to the X. And obviously in this case, X would equal 2. A reminder, you could take the natural log of both sides to actually solve it mathematically and divide it back the other way. Equal 2. So that is, if you maybe don't have pretty numbers or something like that, that technically is sort of how you can sort of solve for the orders. The overall order of the reaction is found by adding the orders together for the reactants. So the overall order is found by taking those guys and adding them together. Once you really determine the rate law, you then can use the same table to figure out the value of the rate constant. And as we talked about, it's called a rate constant, which means for a particular reaction, it should be a constant value. So that means you could actually go back to the table and choose any of the entries, put the values in, and you could solve for the value of K and actually get the value of K there. Some of the benefits are ways that you could think about orders is, again, the proportion of those reactants that will kind of deliver a particular rate. And depending on the orders of the different reactants, one may be more impactive than another in terms of how it affects the rate of a reaction. So I think we did just some generic examples where, if we cut the concentration of this reactant down, how does it affect the rate? Or if we increase the concentration of one of the reactants, it could affect the rate. And we also can have an order that's 0 order. And again, as we saw, I think it did an example there. If you have something that's 0 order, you could play as much as you want with that concentration. It's not going to have an impact on the overall rate of reaction. So, those orders are important in terms of getting an understanding as to which reactant is maybe, I don't want to say most important, or important in terms of the overall rate that's occurring. Any questions on any of that stuff we talked about there? So I think we kind of did this one last time, and it's where we finished up, and we did get the rate law here. So just to kind of finish up a little bit of the calculation on this one, again, this is where we chose 2 entries. We ended up getting our orders, and we saw that it is second order overall. At this point that we have the actual completed rate law, this is where we can then go back into the table and we could solve for the actual value of the rate constant. So in this particular case, if we take this rate law here and we rearrange and solve for K, K would equal the rate divided by the concentration of F2 and the concentration of ClO2. And I'm getting that by just rearranging this equation and solving for K, basically dividing everybody to the left-hand side of the equation. Now I'm going to actually just choose the very first entry in this table, and I'm just going to put the actual values in for it. So the rate was 1 times 1.2 times 10 to the minus 3 molar seconds divided by our concentration of F2, which was 0.1 molar, times our concentration of C. And if I solve for that there, we get 1.2 exponent button negative 3 divided by 0.1 divided by 0.01 gives us a rate constant value of 1.2 in this case. The units here would be what? Would the units here be? Molarity up on top will cancel with the molarity on the bottom, and that leaves you 1 over molar seconds as the units that are associated with that. Or you could write 1.2 m to the minus 1 s to the minus 1, whichever way you want to do that. As we will see, those are the typical units that are associated with a second order reaction overall. And one of the important things of kinetics is when you are given the rate constant or figure out the rate constant with the units associated with it, you could actually know what type of reaction you're dealing with. Is it a first order reaction, second order, zero order type reaction? Any questions on that? Now, I chose all the information from experiment 1, but you could have done it with experiment 2's information in the table. Could have done it with experiment 3's information in the table. The only thing you can't do is mix and match. So you got to use all the information, obviously, from one entry in the table. Question on that there. Okay. All right. So a couple of things about rate laws that we just saw there. Rate laws are always determined experimentally, and you do need to show some type of work as to how you figure out the orders, and mathematically is probably the best way. Reaction orders are always about the reactants, really not the products, and the order is not the coefficients in the balance equation. So as you can see here, the order for ClO2 is 1, but it's coefficient of 2. So again, in this case, that is not how we actually get those orders. All right, so let's try some here, I think, or do some calculation. A rate equation for the reaction of NO is the rate is equal to KNO times O3. If the rate is 6.6 times 10 to the minus 5, when the concentrations of these guys are what's given, what is the value of the rate constant here? So take a moment and calculate the value of the rate constant based on the rate law that was given to you here. And rolls down here. So in this case, it actually gave us the rate law here, which is the rate is equal to K times NO and O3. By the way, in this case, that would mean the order with respect to NO is what order? The overall order is 1 plus 1, right? Which is second order. Each of these guys has nothing written, so they're each first order, right? With respect to each of the reactants that are present. In this case, they gave us the value, so we just need to solve for K. So K in this case would be the rate divided by NO, and O3, again, dividing these guys to the other side. Putting in our values here, we end up with something 6.60 times 10 to the minus 5 molar seconds divided by R1 times 10 to the minus 6 molar and R3 times 10 to the minus 6 molar. Making sure again that you use your exponent button so you are not off. Divided by 1 exponent negative 6 divided by 3 exponent negative 6. Going to give us 2.20 times 10 Thank you. 7, I believe. Units here would be molarity would cancel again. So once again, 1 over molar seconds would be the proper unit here. Any questions on that one there? Yeah. I get it because if we just look at the units up on top are molarity divided by seconds, divided by on the bottom molarity and molarity. So basically the molarity up on top cancels the molarity on the bottom, and this is basically on the bottom. And that means that we end up with 1 over molar seconds. Yeah. If we wrote it as -1, is that all? It wouldn't be acceptable if you wrote it like that, if that's what you're asking, because that would imply that it's just the seconds that's -1. So you would need to do it for both of them. Yeah. And then that would be fine. Yeah. Second order overall. Yeah. Yes. Yeah, so typically this would be either you would be given the information like you were here. Most likely will be like the table we just did or did the other day. You'll be given that sort of experimental information. And usually the common questions that you're asked when you get a table like that is, what is the completed rate law with all the orders? What is the value of the rate constant? And like, what's the overall order of the reaction? So most of the time will probably be wrapped into like a table type question, but you might have like a standalone question like this as well. Yeah. Yes. But also why the rate law is in it's really not to 0. So in chemistry, if there's nothing written, it's assumed to actually be 1. So even though there's nothing written here, it's actually 1 on for each of those. If it was 0, they would actually write 0 on top of it. So they would write something like, they actually probably wouldn't include it, but if they did include it, they would write actual 0 there, like that. But if you do not see anything there, like we did here, it's assumed to be 1 in this case. Yeah. So just like when we write something like, say, sodium chloride, there's no numbers down here. It's assumed to be 1 of each of those, right? That's the same idea. Yeah. Yeah. Other questions? Okay. All right. So why don't we try this? Let's do it all here. Let's get the completed rate law with the orders. Let's do the value of the rate constant. And let's figure out what the overall order is based off of this table here. All right, so take a few minutes or so, see what you come up with. Looking for those 3 things. What is a completed rate law? The value of the rate constant once you completed the rate law, and what the overall order is. How you're doing. So again, when we have a table like this, we do want to kind of use that rate 2, rate 1 equation that we've been talking about. And again, here we do want to just sort of grab 2 entries where one will remain constant and the other will vary. So just looking at it, I can see entry 1 here and entry 2 will keep our S2O8 constant, and it will vary the other one. So that is what I'm going to choose. In this case, I'm actually going to put everything from experiment 1 up on top, since it does have the larger rate. And again, that will usually sort of give you a little bit more whole numbers than decimal type numbers. You could actually do it either way. It doesn't matter, but just a little easier to visualize sometimes. So what I'm going to do is look at experiments 1 and 2 here. And putting everything from experiment 1 up on top, 2.2 times 10 to the minus 4 equals our rate constant, 0.08 to the x and 0.034 to the y. Obviously filling in our concentrations. Putting everything from number 2 on the bottom gives us 1.1 times 10 to the minus 4, our k. 0.08 to the x and 0.017 to the y. Doing some math here, that's going to cancel out to a 2. Once again, as we talked about last time, although we do not know the value at this point, the k on top and the k on the bottom is the same value because it's a constant. So they should cancel. Once again, here at this point, we may not know what the value of x is, but it's the same reaction. So they should be the same order, which means that really these guys would completely cancel out as well. That leaves us this, which will be a 2 to the y. And once again, here you could just kind of see probably that y is equal to 1, or you can take the natural log of 2 and divide it by the natural log of 2, which will get you 1 as well. So y is the order with respect to I minus. We now will go back to our table, and since we varied I minus the first time, we now want to keep it constant. And to do that, it looks like 2 and 3 will keep the concentration of I minus constant, while the other one will vary. In this case, same deal. I'm going to pick the one that has the larger rate. So that looks like experiment 3. So I can put all of experiment 3 up on top, which would be 4.4 times 10 to the minus 4 equals k times 0.16 to the x and 0.017 to the y. Now I'm going to put everybody for experiment 2 on the bottom. That'll be 1.1 times 10 to the minus 4 k, 0.08 to the x and 0.17, sorry, 17 to the y. All right. We got the numbers in there, right? So this will be 2.817. All right, so 0.017. All right, so dividing here, that looks like perhaps a 4. Once again, the k's are going to cancel. These is going to give me a 2 to the x, and these guys will completely cancel. And here, x would then equal 2. Once again, you can take the natural log of 4 divided by the natural log of 2 if you cannot see it. So the order with respect to S208 is second order. That means our completed rate law at this point would be something like the rate is equal to K times S208 2 minus to the second and I minus to the first. First off, any questions on any part of that calculation there? Yeah. And it doesn't really matter truthfully which one you do, but most of the time, if you take the one that has the larger value for the rate, it oftentimes will give you more whole numbers than decimal numbers. If you do it the opposite, you'll come up ultimately with the same order. It just you'll be dealing with sometimes decimal type numbers. So it's just sometimes easier to see the number if you kind of do it that way. But yeah. How did I on which one? I'm sorry. Which? Mhm. Yeah. So basically, if you on your calculator took this number, these two numbers, and divide it, it should equal 2. And if you divide basically 0.08 divided by, I'm sorry, 0.034 divided by 0.017, it should equal 2. And then the exponent part would still stay up on top. And then at this point, basically 2 to the first power, right, is basically 2. So that's what y would equal. And again, really mathematically, if you wanted to solve, if you weren't sure and it wasn't like a number where you maybe could visualize it, you could take the natural log 2 on the left and take the natural log on the other side. And when you take the natural log on the right-hand side, it actually will bring the y down to like a regular letter, if you will. It's not an exponent anymore. And then what you would do is divide natural log of 2 to both sides. These would cancel, and then that would equal basically in this case 1. And you would do the same thing here. You could take the natural log of 4 is equal to the natural log of the other side, which would then bring the x down. You could divide the natural log of 2 to both sides. And then this will actually equal 2 in that case as well. So if it's a number you can't visually see, and sometimes it happens, it's maybe not perfectly pretty number or something like that. Or maybe you did the decimal version where you kind of did the lower rate up on top. You may have to do that sort of calculation on both sides. Any questions on that? Okay. So now that we have the rate constant with its orders, we could figure out the overall order. And that would then be 2 plus 1, which means this is actually a third order reaction. As a result of that, again, just adding up the orders that we see here. And the last thing that we need to do is, now that we have the actual rate constant, we could solve for the value of K. And that's just going to be found by rearranging our equation there. I'll erase a little, get some room here. So if we rearrange our equation in this case, the K would equal the rate divided by the concentration of S2082 minus, and that is squared, divided by the concentration of I minus. So once again, you could choose any one of these entries in the table to solve for K. I'm just going to choose, why not? I'll choose number 2 for fun. We'll put number 2 in there. So K would equal 1.1 times 10 to the minus 4 molar seconds divided by 0.08 molar, and that is going to be squared. And we're dividing it by 0.017 molar. And if we do all that there, 1.1 exponent -4 divided by 0.08 squared divided by 0.017 gives us, I believe it's a 1.01 if I'm reading my calculator right. Gives us a value of 1.01. In this case, the units would be what? Once again, we do have a molarity up on top and a molarity on the bottom that will cancel. We'll leave us with 1 over molar squared seconds. Again, the square goes for the number and the unit, right? So you got to make sure that gets in there as well. Question on that there. So the answer to our earlier question, this is probably typically, the questions that you'd be asked about finding the rate constant through a problem like this, where you kind of have to go through the whole process there. The process of obviously calculating these things is you got to get the completed rate law with the orders first before you could get the value of the rate constant. And then you get that kind of at the end, or the overall order as well. Any questions on any part? Yeah. To solve for the rate constant, is that what you're asking? You can choose any of the experiments you want. They all should ideally come out the same.
For the completed rate law, do we always choose like 1 and 2 and then 2 and 3?
No. So it just depends on the entries. So what you're looking for is any 2 entries, and it doesn't matter what the experiment number is. Any 2 entries where one stays constant, the other one varies, the concentrations. That way you don't have too many unknowns or anything like that. All right, so let's try perhaps another one here. All right, so let's give this one. Let's do the same thing. Let's do the completed rate law. With the orders, let's do the value once again of K, and let's do the overall order here. So this one you have 4 entries. So again, you just want to pick through the table, looking for 2 that have 1 constant and 1 that. Okay, let's take a look. So in this table, we got 4 entries, and it really doesn't matter how many entries you have. You could have a bunch of entries. But we're really looking for, like I said, 2 entries where one stays constant and one varies. In this particular case, just looking at it, we could go with experiments 1 and 2, and that will keep our CO here constant while varying our other guy. So that is what I'll start with, experiments 1 and 2. You could also do 1 and 4 in this case, since there was another entry and it should come out about the same. So you could do that as well. So 1 and 2 here, I'm going to go with number 2 up on top since it has a larger rate. And that's going to be 0.0082 equals K times 0.2 to the X and 0.1 to the Y. So that is all of experiment 2's information. Experiment 1's information will go on the bottom here, 0.0021, RK 0.1 to the X and 0.1 to the X to the Y. All right, so dividing this out here, we get 0.0082 divided by 0.0021. And we do not get a nice pretty number. We get 3.9048. This will cancel. These guys here will give us a 2 to the X. And once again, these will completely cancel because those guys are the same. In this case, you might want to do a little natural log of both sides. So you could do a natural log of the 3.9048 equals natural log of 2 brings the X down. I'm going to take the natural log of my entire number I have on my calculator and then divide it by the natural log of 2. And again, dividing the natural log of 2 to both sides gives us an X value of like 1.97, which, since this is an experiment, pretty close to 2 in this case in terms of rounding. Any questions on that there? Okay, in this case, then we're going to go back to our table and find a blank screen. We're going to find one where we're going to keep the NO2 constant. And in this case, it looks like you only have one option where you could do that. And that's going to be experiments 2 and 3 is where those guys are going to stay the same. So looking at experiments 2 and 3 here. In this case, it's not that big of a difference, but I'm going to put number 3 up on top, which is 0.0083. And that means I have a K 0.2 to the X, 0.2 to the Y, divided by 0.0082 RK, 0.2 to the X, and 0.1 to the Y. Once again, that is pretty close to 1, I'm assuming, but divided 0.082. Going to give us like a 1.0122 is equal to, once again, these guys are going to cancel. This is going to completely cancel out, and this is going to give us a 2 to the Y. Once again, if you want to do a natural log of both sides, you can. Natural log of 2 to the Y. And once again, we're going to divide that to the other side. And that's going to give us the natural log of that divided by the natural log of 2. In this case, 1.7, and that's pretty close to 0. Yes. In this case, if you ended up rounding here, right? Anything to the 0 power equals 1, basically, is where we're at there. Yeah. Any questions on that there? All right. So at this case, our completed rate law would actually be the rate is equal to K and the concentration of NO2, and it would be squared. And now, because CO is to the order of 0, you do not need to put it in the rate law because it basically equals 1. Or if you do put it in the rate law, you do need to put the 0. Otherwise, if you don't put the 0, it implies the order is 1. Yeah, so you would have to put it in there. So you can either write the rate law like this, which is probably what most people would do, or if you did want to put the other one in there, it is really important that you did it like this and actually put the 0 there. Again, if you left it blank, people would look at it and assume that it's first order, which it is not. So my opinion probably would roll with a rate law like that, so you don't accidentally mess up yourself looking at it. The overall order here in this case would be second order, as is 2 plus 0, which would be second order. Any questions on that so far? So really, yeah. Are you asking why you cannot write like a CO with a 1 up on top? Is that what you're asking? Or yeah, you cannot, because that 1 would imply that the order for CO is first order when it's really 0 order. Because it's 0 order, this entire thing equals 1, not the order. Yeah, so anything taken to the 0 power is equal to 1, basically. Other questions? Okay, so we will rearrange our rate law and solve for K here. And in this case, K would equal the rate divided by NO2. And once again, we do need to square it. You could choose, again, any of the entries in the table to do this. I'm just going to roll with number 1 there, because why not? So we're going to go 0.0021 molar seconds divided by 0.1 molar, and then we're going to square it. And that will give us 0.0021 divided by 0.1 squared. And that gives us something like 0.21. Units here would once again molarity up on top, and one of the molarities would cancel, gives us 1 over molar seconds, which is typical units of a second order reaction, which is what this one is. Any questions on that there? So this one didn't have necessarily pretty numbers. It is okay, like we did there, to round if it's really close to the whole number. Is that your question? Or yeah, okay. So it is okay to round if it is really close to a whole number. Remember, a lot of these tables technically are based on experiments, so experiments are not going to be perfect, right? Although a lot of book problems sometimes did just come out very perfect, nice whole numbers and stuff like that. If it's really far away, you probably shouldn't round, but if it's really close, you should round. Other questions on that? Yeah. Yeah, because the answer is there's really no way to find K until you know the orders. And so you have to actually get the rate law first in order to find K, because you won't know what to, if you should square it or not square it, those type of things. Yeah. Other questions? So yeah, that definitely is the process in these type of problems, is get the individual orders, write the complete rate law, and then get the rate constant at the end. Other questions on that? Yeah. 1.97. Yeah, I would say probably you should round to the whole number. I don't know personally if I would probably dock you on that. I would say a lot of times orders are whole numbers. They could be necessary, not whole numbers, but most of the time people will put it round to the nearest whole number if it's close. Yeah. Other questions? Yeah. All right. Let's try one more here. See, to close it out, I think, for today. All right, same thing, solve for everything. Value the rate constant, the orders, the rate law, all those good stuff. All right, let's take a look at it since we're getting to the end here and see how you're doing. So once again, we're going to choose 2 of the 4 entries here. And it does look like we could roll with 1 and 2, as those guys will stay constant. So we're going to do our rates. And we are going to put rate number 2 up on top, since it's 32.3. By the way, you hopefully did not ignore this part of it right there, which is times 10 to the minus 7. because that will affect your answer at the end, probably. You'll be okay. Just that little extra information. It's not that important. You'll only be wrong at the end, I suppose. So let's see here. So we're going to do number 2 and number 1. I guess our 1 and 2 is the other way people usually say that. So we're going to go number 2 up on top, which would be 32.3 times 10 to the minus 7 is equal to K times our 0.06 to the X and our 0.2 to the Y. That is going to be divided by 10.8 times 10 to the minus 7, RK 0.02 to the X and 0.2 to the Y. Dividing 32.3 divided by 10.8 to the minus 7, it does give us basically 2.99, which I'm just going to kind of round to a 3 at this point, I hope. And that is going to get rid of that. That will give me a 3 to the X, and these guys will completely cancel out, and that would be X is equal to 1. Once again, here you could keep the 2.99 and divide it by the natural log of 3, and you'll get 0.997, which is basically 1 as well. So if you did the natural log, you'll end up with 0.99, something like that, which is basically 1. Any questions on that? Now, if you screwed up there and didn't use the times 10 to the minus 7, it worked out because they canceled, but not for the rate constant. It doesn't cancel. So you'll be off on that number. So you got lucky on half of it. Might not be as big of a line when we get there and grading it. So that is 3 and 4. We'll do that. Okay. So we'll do 3 and 4. I'm going to put the 21.6 guy up there on top since it is the larger number. And we'll put number 3 on the bottom there, which is 10.8 times 10 to the minus 7, K 0.2 and 0.0202 to the Y. So again, 21.6 divided by 10 error. No, 20. Oops, come back. Whichever way I went there. Went some way. There you go. There it is. 21.6 to the negative 7 divided by 10.8 gives us a 2. These guys will cancel. These will completely cancel. And in this case, it will give us a 2 to Y, which means Y is equal to 1. So in this case, our rate law would be the rate is equal to K NH4 plus and NO2 minus. Again, by not writing any numbers above those guys, it's assumed to be 1 for each of them. The overall order here then would be 1 plus 1, which is second order. And now we're ready to solve for K. So K here would be the rate divided by our concentration of NH4 plus and our NO2 minus. So just basically taking these guys and dividing it to the other side. This is the situation where you will be off, obviously, if you ignore that. So this would be 10.8 times 10 to the minus 7 molar seconds. And I'm just choosing number 1 here to do it. We'll do 0.02 molar and 0.2 molar there. And that will get us 10.8 to the minus 7 divided by 0.02 and divided by 0.2. Going to give us 2.7 times 10 to the 1, 2, wrong way, 1, 2, 3, 4, minus 4. Units here, molarity up on top, molarity on the bottom cancel, leaves us 1 over molar seconds, which is typically what we see for a second order equation there. Any questions on how to calculate the rate law? Yes. Yeah, you could choose any entry to figure it out. They also come out the same because it's a rate constant. So it should be the same value for all the experiments. Yeah. Other questions? Yeah. Everybody have a seat for a second, relax. Molar seconds. The rate constant units does change depending on the order of the reaction, and we'll talk about it later on in the chapter. Yeah. Is there a question in the back or no? Good. No?